Hello 347 fans. This video is going to examine first order differential equations and how to solve them using the antiderivative. This will be known as the first flavor of differential equations that we can find an expression for the solution. We'll talk about some motivation for these types of equations, talk about solution families, and then we'll see how the fundamental theorem of calculus applies in a couple of different ways. So we've been studying this first order differential equation here written in normal form, x prime equals capital F of t comma x. I want to remind you that as we saw at the end of last section, this information gives us the slope of the differential equation. Now that's cool, but what we're really looking for here, hopefully, is an expression for the unknown function. In this particular differential equation, the unknown function is x as a function of t. Now, I want to point out that there's a category of first order differential equations, x prime equals little f of x, that are called autonomous. You know a differential equation is autonomous if the independent variable, so in this case t, doesn't explicitly appear on the right-hand side of the differential equation. We're going to talk more about autonomous differential equations in section 1.5, but I want to point that out here because the methods that we talk about in this section on antiderivatives are not applicable to autonomous differential equations. So you know a first order differential equation is categorized as integrable if it can be written as x prime equals g of t. So compared to the autonomous case, an integrable case has a right-hand side that only depends on the independent variable t. I want to remind you that it's going to be useful to go back and forth between Lagrange or prime notation and Leibniz or dx dt notation. So keep in mind that here, usually our independent variable is t, so x prime means a derivative with respect to t. So let's think about this critically a little bit. Given this differential equation, x prime equals g of t, how might we find the solution? Well, here by a solution, we meet a function x such that when you take the derivative of that function, you get back g. That's just another way of saying that x is an antiderivative of the function g. And you can see that more clearly by having a look at this differential equation in Leibniz notation. So if we rewrite the differential equation with Leibniz notation, dx dt equals g of t, and think about integrating both sides with respect to t, then we see that the solution, x, is the general antiderivative of g. Okay, the indefinite integral of g. Now, as you can see, this incorporates a constant of integration, capital C, and it ends up that that's going to give us a family of solutions. Okay, so once again, the integrable differential equation x prime equals little g of t has solution x equals an antiderivative of g plus c, or sometimes we just call this the general antiderivative, right? If you lap plus c onto anything, we sort of think of that as the general antiderivative of g. Now, on the other hand, if you're given an initial value problem, that is, you know the value of the unknown function x at some time, x of t naught equals x naught, all we have to do is identify the correct constant c such that when you substitute t equals t naught, the value of x is equal to x naught. So here's an example that shows how to solve an initial value problem of an integrable differential equation by finding an antiderivative. So in this case, we have x prime equals t squared minus 1, where the value of x at t equals 1 is 2. So x of 1 is 2. Okay, so here it's pretty quick just to integrate both sides with respect to t, or in other words, the general solution here of this differential equation x is the general antiderivative of t squared minus 1. Okay, so integration of polynomials is something we know how to do. We can think about, again, this differential equation rewritten in Leibniz notation and just integrate both sides. The integral of dx dt with respect to t is x of t. And an antiderivative of t squared minus 1 is 1/3 t cubed minus t. Slap on the plus c to get the general solution. Now we're interested in solving an initial value problem here. So we're interested in a function x such that when you plug in t equals 1, right, substitute 1 for t, it's equal to substituting 2 for x. Okay, so here we see a substitution of t equals 1 and x equals 2 into this general solution of the differential equation. And just a little bit of fraction algebra gives us c equals 8/3. So here's the solution of the initial value problem, 1/3 t cubed minus t plus 8/3. Of course, this function is differentiable for all t, so the interval of existence is all t from minus infinity to infinity. For what it's worth, here is the solution family, right? So the general solution is a cubic, and in this case, the plus c ends up corresponding to a different y-intercept, or in this case, an x-intercept. Um, we see here the solution that goes through 2 when t is equal to 1. And just to connect further with the topic from last section, here's the slope field of this differential equation. Okay, here's another differential equation. Now this is a second order differential equation, but it similarly has right-hand side that's only a function of t. So we can use methods of this section to find a solution of this differential equation also. As you might expect, a second order equation would require you in some sense to do two integrals. So there ought to be two constants of integration in the general solution. So we expect here a two parameter family of solutions for the general solution. So we can first solve for the derivative x prime by just integrating the second derivative x double prime. So again, integration of polynomials isn't so hard. And with the intuition that we're going to have a two parameter family of solutions in the general solution, in this case, I've tacked on a C1 to identify the general solution, x prime of t. Now, similarly, we can integrate x prime to get an expression for x, and we can see that here, C1t plus C2 at the end of the integral. And again, we see the two parameter family of solutions. I haven't said anything about the interval of existence, but of course, polynomials are differentiable for all values of t. So in this case, the interval of existence would be all values of t. Okay, one more example, just to sort of illustrate an idea that's going to come up again later. So we'll find the general solution of this differential equation, x prime equals e to the minus t squared. Now, this function e to the minus t squared is a function that comes up for us in Calculus 2. And one of the reasons we talk about it in Calculus 2 is because it's a function that has no elementary antiderivative. So just as a review, a function which has no elementary antiderivative is a function for which no other function can be written in terms of our normal functions, in terms of sines and cosines, powers of t, exponentials, logarithms, so on and so forth, such that the derivative of that function gives us back the function in question. Okay, in other words, we can't find a function such that the derivative is equal to e to the minus t squared. Okay, so in this case, we just write the general solution of this differential equation as an integral, tack on a plus c for the general solution, and leave it. Now, this differential equation is going to come up again a little bit later, so we'll come back to this idea of expressing the solution of a differential equation as an integral a little bit later. Okay, want to go ahead and incorporate the fundamental theorem of calculus as a review. The fundamental theorem of calculus applies to a function x of t, which can be written as an integral from some constant a to t of some other function g of s ds. We prove in calculus that when g is continuous on the closed interval, then x is also continuous on the closed interval. It's differentiable on the open interval, and the derivative of x with respect to t is actually just g applied, g evaluated at t. So if you have a look at the result of the fundamental theorem of calculus, the form of the result looks exactly like our integral differential equation. Okay, so this suggests a strategy to solve an initial value problem that's expressed as gx prime of t equals g of t. And here's the strategy for solving this initial value problem. We'll go ahead and introduce a dummy variable of integration, and then use definite integrals on the interval from t naught, which is the t value corresponding to the initial value problem, to t. So of course, on the left-hand side of this differential equation, antiderivative of x prime of s ds is just x of s. Fundamental theorem tells us that this should be evaluated from t naught to t. And similarly, we can express the right-hand side as a definite integral also, the integral from g of s ds from t naught to t. And again here, I'm just using a dummy variable of integration. Remember that with definite integrals, that variable of integration is just a dummy variable. So we can quickly solve for the unknown function x of t by applying the initial condition x of t naught equals x naught and rearranging the differential equation. So just as a check, it's really quick to see that this expression, this integral expression, x of t, is the definite integral of g of s ds from t naught to t plus x naught, is a solution of our initial value problem by just plugging it in to our initial value problem. So on one hand, the derivative of x prime is the derivative of the integral, and by the fundamental theorem of calculus, the derivative of the integral is g. Of course, the derivative of x naught is 0, it's a constant. And if we evaluate this expression, this integral expression for x at t naught, we end up with an integral from t naught to t naught. Of course, an integral from t naught to t naught of any function is equal to 0. So the initial value is satisfied as well. So mathematicians love to do this, try out our new method on a problem that we've already solved. So here again is that first order initial value problem, x prime equals t squared minus t, where x of 1 is equal to 2. And we'll go ahead and illustrate how to solve this using definite integrals and the fundamental theorem of calculus. Okay, so again, we'll introduce a dummy variable s, expressing the differential equation in Leibniz notation. Dx dt equals t squared minus 1, and we'll integrate dx ds from 1 to t with respect to x to s, and similarly integrate s squared minus 1 from 1 to t with respect to s. So on the left-hand side, of course, the integral of a derivative is just the function evaluated between 1 and t. And we know how to find an antiderivative of s squared minus 1 and evaluate at the limits. And you get the expression shown here, 1/3 t cubed minus t minus the quantity 1/3 1 cubed minus 1. And of course, when we apply the initial condition, x of 1 is equal to 2, and simplify the right-hand side, we end up with x of t equals 1/3 t cubed minus t minus 8/3. Typo here, of course, that should be plus 8/3. The solution is 1/3 t cubed minus t plus 8/3. And of course, like before, the interval of existence is minus infinity to infinity, as this function is differentiable on the interval from minus infinity to infinity. Okay, to return to this function for which there's no elementary antiderivative, I'll go ahead and express the solution of the initial value problem x prime equals e to the minus t squared, where x of 0 is 2 in terms of a definite integral. We proceed the same way using a dummy variable of integration and then integrating from the initial value in the independent variable, which in this case is 0, up to t. So the integral of x prime of s ds from 0 to t ought to be equal to the integral of e to the minus s squared ds, again from 0 to t. Now the integral of the derivative, x prime, is just the function x, and we'll go ahead and evaluate that between 0 and t, and that should be equal to this function for which there's no elementary antiderivative. Now it turns out that this integral of e to the minus s squared ds comes up a lot. It's really important in probability and statistics, for instance. Integrals like that one have a special name. They're related to the error function. So the error function has a multiplicative constant in front of the integral, 2 over the square root of pi times the integral from 0 to t of e to the minus s squared ds is the error function. So we can actually express the solution of this initial value problem in terms of that error function by manipulating this definition of the error function. So in this case, we see that the integral from 0 to t of e to the minus s squared ds is equal to the square root of pi over 2 times the error function of t, so that x of t, once we substitute x of 0 equals 2, can be expressed as 2 plus square root of pi over 2 times the error function. The error function turns out to be a perfectly good differentiable function on minus infinity to infinity. So again, the interval of existence in this case is from minus infinity to infinity. An integral equation is not a differential equation. Obviously, it's an equation involving an integral of an unknown function. And it turns out we can use the fundamental theorem of calculus to have a look at integral equations also. Just as a reminder here, I've written the fundamental theorem of calculus in a slightly different way, but if capital F of t is an integral from t naught to t of g of s ds, then we can introduce a derivative by just taking derivatives of both sides. F prime of t is equal to g of t by the fundamental theorem of calculus. Moreover, a strategic choice of t, you might try t equals t naught, simplifies an integral equation quite a bit and will end up giving us an initial condition. So to illustrate this strategy, we'll go ahead and have a look at the integral equation, x of t plus an integral from 0 to t of e to the minus a times the quantity t minus s times x of s ds equals b. So again, this is an integral equation because it's an equation involving the integral of an unknown function, which in this case, again, is x. So we'll see how to transform this into an initial value problem, a first order initial value problem, and later we'll see how to solve that initial value problem for x. So in order to transform this into an initial value problem, we'll begin by manipulating the integral a little bit. As you can see, the function of t underneath the integral is constant with respect to the constant of it, to the variable of integration s. So we can use properties of the exponential function to factor out e to the minus at. Once we've done that, we can introduce a derivative, just taking the derivative of this expression, x of t plus e to the minus at times an integral from 0 to t of e to the minus as x of s ds equals b with respect to t. Okay, of course, the derivative of x is just x prime. And then to differentiate the second term, we use the product rule and the fundamental theorem of calculus. So here we have e to the minus at times the derivative of the integral expression plus the derivative of e to the minus at times the integral expression. Now the derivative of the integral expression is quick just by the fundamental theorem of calculus, and the derivative of the exponential term just requires the chain rule, and we can see that here. We end up with x prime plus e to the minus at times e to the at x of t. That term in the square brackets is due to the fundamental theorem of calculus. minus a times e to the minus at, that's the derivative of the exponential term, times the integral expression equals 0. Now, at first glance, it doesn't look like we've made our life any easier, but manipulating the third term in this expression, the term involving the integral, we can express it as the integral from 0 to t of e to the minus a times t minus s, x of s ds, which is exactly equal to b minus x of t from the original integral equation. So finally, we end up with a differential equation, an equation involving a derivative of an unknown function, which in this case is x of t. So again, we'll go ahead and just express that as a first order differential equation, x prime plus the quantity 1 plus b times x equals a times b. Now we're not quite done yet because we've been asked to transform this into an initial value problem. And remember that an initial value problem is a differential equation together with an initial condition. So choosing strategically, we see that the choice of t equals 0 simplifies the integral term significantly. So if we substitute t equals 0, we see an initial condition x of 0 equals b. That gives us the initial condition for the initial value problem, which we've written here. So again, we've been able to transform this integral equation into an initial value problem via the fundamental theorem of calculus. It turns out that the differential equation in this initial value problem is a special form that we'll see how to solve in a couple of sections. Okay, thanks for your attention to this video, folks. A lot of information here about solving first order differential equations which are integrable using antiderivatives. And we've seen how to use definite and indefinite integrals, as well as how to apply the fundamental theorem of calculus in order to do that. So long for now, and we'll see you next time.